So first, to begin use of a mass spectrometer, you need to ionize your sample in some way, shape, or form. And so the very earliest mass spectrometers actually started with things that were already in the gas phase, GCM, some sort of GCMS. So that's why that initial mass spectrometer result that I showed you on the very second slide, I think, was with neon 20 and neon 22, because it was already gas phase. And they could do really intense or so-called hard ionization of the gases by bombarding or hitting them with electrons. However, those techniques aren't as useful for biologics and the molecules we're interested in proteomics. And so we have a number of different ionization sources. The most common is electrospray ionization for use with LCMS, but also atmospheric pressure photoionization, atmospheric pressure chemical ionization, and then the GCMS for the harder ionization. I'm not going to get into the atmospheric pressure ionization modes too much, just because we're not using them a lot, because these are for the non-polar molecules. So if you are studying something like lipids or things that can be in the gas phase, some small molecules, it's really useful to have these forms of ionization. But for peptides and proteins, we're using mostly ESI and MALDI, which are the soft ionization techniques that won a Nobel Prize in 2002. So this is just a little bit of a summary of how these different forms of or sources for ionization are chosen based on what it is you're trying to study, and how the sample is ionized can result in different flavors of ions. So ESI, or electrospray ionization, forms mostly multiply charged ions, whereas APCI and APPI are more likely to form singly charged ions. This is just important for how you're going to analyze the data. And many compounds will ionize using any of these sources for ionization, but APCI and APPI are specifically more useful for things that are less polar or non-polar. Electrospray ionization, which I mentioned before, is one of the most common modes because it allows you to introduce your sample in a liquid form. So you don't have to automatically put your protein into the gas phase. You're running it across a column, doing some sort of liquid chromatography first. And at the very end of the column, there will be what's called an emitter. It's a very fine tip. And as the column is flowing slowly, you create this cone of desolvation where you're approaching you have some nebulizer gas, which is helping the solvent molecules evaporate, and your molecules of interest ionize and go into the gas phase as ions. There can also be some fragmentation that occurs in this form of ionization. So in some situations, you will see, instead of an intact peptide or molecule, you may fragment it if the voltage is too high on this emitter. And so this is called soft ionization because your compound is ionized while it's in solution. You've already added acid or base to make it an ion, and it is just nebulized softly into the gas phase. It may or may not use this nebulizer gas, and it's easily coupled with liquid chromatography. And so we're actually doing nanospray ionization down in the proteomics core here at IU, and this is just an image of how tiny this emitter is. And we're running at flow rates of maybe 300 nanoliters per minute. So you can imagine how slow that is and how tiny of a little droplet is forming at the tip of this emitter over a course of a minute.
Yeah,
and that's how we're introducing.
Sometimes it's fun to talk about most of the students have pipetted like half a microliter. So if you can imagine pipetting up half a microliter and then trying to spread that out over a minute, then it's really easier to try to think about how small these flow rates are. So
exactly. So you can imagine nanospray. There was just a paper actually recently with pico spray, in case nanochromatography isn't difficult enough for you. But another mode of ionization, another source that I wanted to mention briefly is MALDI, which is matrix-assisted laser desorption ionization, and it's another soft ionization approach. And in this situation, you are spotting your sample mixed with an analyte of some sort, and then you actually hit it with a laser beam, and the matrix transfers charge to your analyte ion. And as it's broken up off of this surface where you've spotted and dried your sample and analyte, it can then go into the mass spec. And in the case of MALDI, you mostly end up with singly charged ions, and you're mostly looking at these larger intact masses. But it's also a really useful and very important tool for biological mass spectrometry.
And MALDI's become something that's taken off again in the area of imaging mass spectrometry, which unfortunately we don't have time to talk about in the course. But if anyone's interested in that type of stuff, there's a lot of research being done in that area, and it's something you could look up, just imaging mass spec. And it's a way to be able to take sections, like let's say a section of a brain, and be able to look for particular molecules using mass spectrometry, some that might be like lipids or other small molecules that you can't detect necessarily with antibodies. So just interesting to think about.
Yeah, so a really important technique that we're not doing a lot of, and I'm not going to get into in too much more detail, although I do have an example of a MALDI spectrum later on in the talk. So definitely worth looking into or keeping in mind for your research. So after you have managed to ionize your sample, you need some ion optics, ion guidance to get the sample from the source to the detector. So this is an example of ion optics throughout an example mass spectrometer. And here you have examples of multiples and lenses, and I'll go into a little more detail about the different modes of action of the multiples a little in the next slide. But essentially, there's a DC offset that occurs throughout the mass spectrometer that, since in the study of peptides and biomolecules, we have positively charged ions, we have increasingly negative voltages applied across the mass spec to accelerate the ions and then eventually capture them where we would like to focus them prior to detection. So throughout the mass spec, there's increasing vacuum, and there's also increasing negative voltage applied to the lenses and the end caps of the multiples to focus and get the ions traveling where we need them to go. And in the last slide, you saw those multiples. An example is a quadrupolar multiple. Here you have 4 rods, so that makes it a quadruple, but there can be octupoles, there can be all sorts of variations of this as an ion optic or a potential mass analyzer as well. And essentially you still have a DC voltage applied to one end of the multiple, but you also have AC applied to each optic. And here you can see opposite poles have opposite polarity voltages, and that creates a frequency allows only certain to transfer through the multiples. So ions that either have too low of a charge or are, yeah.
You cut out a little bit. Could you repeat that, just that last part?
Yeah, sorry about that.
That's okay.
Yeah, no worries. So you can see that there's both DC and AC voltages being applied to a multiple. And at the ends, the DC offsets are, again, what I mentioned before, keeping the ions moving and propelling them down the mass spectrometer through the mass spec. However, on the different rods, each rod, sets of rods have opposing voltages, negative and positive, and these create a frequency where ions of specific mass to charge ratios are transmitted through the ion optics towards the detector. So it's called resonance if an ion is stable enough to transmit through the ion optics. If an ion does not have a charge, or if it's too large, it may go off and either hit one of the rods or go through the ends of the rods. And that's done on purpose because we are trying to just look at a certain segment of the population of ions. Everything that is ionized in the source may not be things that we're interested in. There could be things that only have a single charge, and those are probably not peptides. And if we can get rid of them before they reach the mass analyzer, it gives our mass analyzer a better opportunity to give us good data. So a quadrupole such as this can be used as an ion guide, a mass filter, and a mass analyzer. This is one of the earliest forms of mass analyzers. And now we're going to go through some more recent examples of mass analyzers. These are important in the mass spec, both for ion storage, ion isolation, ion fragmentation, and ion scan out to a detector. And the most common types of mass analyzers are quadrupoles, ion traps, time of flight, FTICR, which is a Fourier transform ion cyclotron resonance, and an Orbitrap. And so each of these manipulate ions in slightly different ways, still applying magnetic or electrical fields to contain ions and then scan them out or allow a detector to determine their mass to charge ratio. The mass spectrometers have been improving their resolution over time, and you can see that a low resolution mass spec has 1 to 0.1 Dalton accuracy, whereas the higher resolution, newer types of mass analyzers include Orbitraps, FTICRs, and hybrids with ion traps. And sensitivity is important. The faster sort of scans that you can do with some of the lower resolution can get you some deeper data. And if you're looking at smaller molecules, this low resolution instrument may be enough for you to get very or pretty precise in terms of the combination of atoms that are making up your small molecules, is what I wanted to bring up. So when I was in grad school, the synthetic chemists were always using just a single quadrupole to check their synthetic chemistry reactions, because they knew more or less what they were looking for, and a single quad could give you good enough data. And a time of flight, or a quadrupole time of flight, would give you high enough resolution in that setting with fragmentation to identify small molecules being made by enzymes. So, it really it just depends. We needed to move to Orbitraps and FTICR when I was doing my postdoc, because we were looking at peptides and intact proteins, where you need the higher resolution, has longer scan times, and it's overall generally slower, although those are things that's what the vendors of mass specs are constantly working on improving, right? There's always something new to buy.
For sure.
So,
thank you.
Not sure if I went the right direction with that for you, but I did want to point out what resolution means and is. And so this high resolution analysis gives you the higher mass accuracy. And so here you have examples of a resolution at 500, 1,000, and 5,000, and you can get more and more precise on your mass accuracy. And that's going from seeing just a peak that encompasses all the different isotopes of a molecule to the specific isotopic composition of an ion. And it can allow you to determine the precise modifications down to really low ppm. So that's just an example of the mass difference between an acetylation and a trimethylation is very small. But if you have a high enough resolution mass spec, you can differentiate very easily. So to go through some examples of the different mass analyzers that I mentioned before, I'm going to talk about all of these just briefly so that you have heard of them and know what they are, and you can go back if you're more interested in some of the physics that happens. An ion trap is traps ions of selected mass range and stores them for analysis or fragmentation. And instead of 4 parallel rods, like we saw with the quadrupole or a multipole, it consists of a circular ring electrode plus 2 end caps that form this trap. And when you're interested in sending the ions out of the trap, you apply an analytical radio frequency ramp. You ramp the voltage up, and as the Q value reaches the resonance with the ions that are in the trap, they're ejected, and you can measure them with the mass detector. And these are, used in combination with many other of the mass analyzers. Dr. Mosley already mentioned that some of our instruments that provide us the most sensitive data analysis are because we can use ion trap in combination with something like an Orbi trap. So we can collect ions. So if something exists only at a really low amount, we can collect it over time before either fragmenting it or ejecting it into an Orbi trap for a mass scan. And then a time of flight is exactly what it sounds like. I think this is, all of these mass analyzers are pretty well named after exactly what they do. So in a time of flight mass spectrometer, ions are transferred through initial ion guides, but then there's an ion pulsar, and these packets of ions are pulsed up. There's a reflectron or a mirror. The ions come back down, and the ions are separated by how fast they're moving. And so they're all going to hit this ion detector at different times based on their mass to charge ratio. And so the smaller ones move faster because the energy has transferred more velocity to them. And so then then they're measured by when they hit the ion detector. And this is an example of a quadrupole time of flight, which is a pretty common Agilent instrument, which we don't have in the core right now, but this was the one that the other bioinformatics core in biochemistry has. I'm going to briefly mention FT-ICR. This is the ion cyclotron resonance. They're less popular now, but they're one of the most high resolution instruments available. And so in the FT-ICR, ions are initially trapped and then excited into their cyclotron resonance. And after the excitation field is removed, then the ions are rotating, and since the excitation field has been removed, they're slowly decaying in energy. And this free induction decay transient is then used to determine the mass spectrum by Fourier transform. And these are big magnets. So I worked with some of these in my postdoc, and you have a minimum of an 8 Tesla magnet, and it's probably the size of like the smallest couch you have in your house. And we had up to a 14 Tesla magnet, and it's big, and it requires a lot of helium and nitrogen to keep it cold enough to be semiconducting while you're doing all of these experiments. So although you can do really high resolution mass spectrometry, it's a pretty expensive and a pretty high maintenance form of mass spec. And constantly be refreshing liquid helium and liquid nitrogen into your magnet, or it could quench, and then it's not really a magnet anymore. So it's pretty expensive, but definitely revolutionized the field when it was made. And what we do have are quite a few Orbi traps. So these, I think it was like maybe 1999 or early 2000s when they made the first commercial Orbi trap, and it's been really fascinating to watch them, get smaller and smaller and easier to use. And in an Orbi trap, ions are introduced, and then they rotate around the spindles with two different electrodes. And as the ions oscillate back and forth around this spindle, again, you're getting this transient, which is again a Fourier transformed into the mass spec. And so this is also a very high resolution mass analyzer, and it can detect all mass to charge ratios simultaneously. So we have quite a few of these down in the core, and they're pretty great. So as we've kind of brought up throughout, most instruments for proteomics applications are some combination of these mass analyzers. Quadrupole time of flight, ion trap quadrupole, ion trap quadrupole Orbi trap. All sorts of different combinations are available from different vendors, and it really just depends on your application and price range to see which sort of mass spec that you can have and use in your research.